Hello, everyone. I would like to introduce our topic forecasting. Firstly, what is forecasting? It is mainly a prediction of a future event, and forecasting is one of the three components of an organization's demand planning, forecasting, and management process. I believe there are two types of approaches to forecasting. We have qualitative and quantitative. And forecasting is also could be an important input to both long-term and short-term planning. In this slide, we can see there are different planning horizons. We have strategic level, which goes from 1 to multiple years, and we have the tactical. And the examples of tactical we have is sales and operations planning, inventory optimization, and demand planning, which could be planned throughout quarterly or monthly, and maybe weekly sometimes, depending on the type of products and the type of business as well. Lastly we have the operations level. Basically, is the short-term forecasting. For example, it could be between days and as well as hours. Next, we have forecasting methods. We could divide it into being subjective, which is oftenly used by marketing and sales team, and we have the objective, which is used by production and inventory planning. The subjective methods can be divided further into judgmental or experimental. Judgmental is basically finding out the truth and looking for the answer through either consumers. And we could say, for example, we have Salesforce surveys. They are closer to the customers, so they are able to find out and the demand, not the exact demand, but an approximate amount which they are used to. We have Delphi sessions or expert opinions as well. For experimental, there is customer surveys, focus groups, and basically we have also the objective methods, which is either causal. There is an underlying relationship or a reason behind why this is happening, such as indicators or time series where they are finding the patterns in the demand, which is an example would be an exponential smoothing, moving average. All methods they have their roles and place within forecasting. So before we produce to our topics, we want to find out what if firms launch new products. Basically, companies they earn significant amount of profit from new products, which is the goal behind every firm. But what if, like for example, the technology we have 47%, which is the highest profit through they get through new products. The second reason products launch new products is because of product life cycle. They shorten every time, and the pricing always erodes. Hence, why discounts are available to products that are getting older. No one wants to buy old products, so everyone is looking for the new ones, especially in technology. So these are the forecasting method that could be used to predict new product demand. So the top three we have customer or market research, and the second one is jury of executive opinion, and Salesforce composite. And for example, the others, which are exponential smoothing and linear regression or simulation, which require quantitative data, I don't think so. They are able to figure out a new product demand since it's depends basically on past data. So every method they differ or by stage or by new product. Basically, companies they use three different methods to forecast new products. Business to business and business to consumer firms they are very different. The business to business firms they have larger and longer forecasting horizon compared to business to consumer firms, which is 18 months and 34 months. This survey has been taken and it's based on 168 companies. We're going to our first topic, which is exponential smoothing. Exponential smoothing is part of the objective methods, which is basically a quantitative method. It looks at the value of the data, and we know that it assumes that the value of the data goes down and it loses value over time, which means the newer observation of demand is given a higher weighting than the older ones. While with increasing time, the weights fall off exponentially, hence the name exponential smoothing. And exponential models, they mix the value of the recent and past data while giving a higher weighting to the new ones or the older ones, depending on the model. In this topic, we're going to look at the basic simple exponential model, which only considers the level, and also Holt's model, which is both trend and level we're going to look at. In this figure, we have types of models. Basically, we have the simple one, which is only the level we are going to look at, and then the Holt is the linear trend one. And there is a more complicated one that is used always in forecasting methods. It's very famous, which is double exponential smoothing model. It's called Holt Winters. It accounts to both level and trend and seasonality. In Holt's winter model, they only look at a larger, longer forecasting horizon, and it's very successful with that because it looks at seasonality and it needs data of over 2 to 4 years to get a perfect forecasting results. And there is damped trend and exponential trend, which could be further explained if you look at the examples. Here we have both the calculations and the equation for both simple exponential smoothing model and the Holtz exponential smoothing model. In the simple exponential smoothing model is very simple. We have the new forecasting model, the new forecasting result that we need to find out, which is equal to the smoothing constant. And here is where the trick happens: is that the smoothing constant figures out which weighing does it give it to? Does it give it to the a newer observation or the older observation? Which is, for example, if the smoothing constant is here, it's multiplied to the observed value, which is the demand that is shown, plus one minus the smoothing constant again, multiplied by the forecasting of the older period. In Holt's exponential modeling, we have three equations and two smoothing constants are used. So the first equation is for the level. The first level is estimated basically as a parameter. It is found out. Then later on, which is this one, and then later on we have it's equal to the smoothing constant multiplied by the observed value, the demand that is observed on that specific period time, plus one minus smoothing constant into the level estimate plus the trend estimate. And here is the equation for the trend estimate. We have the smoothing constant multiplied by the level estimate that we found out minus the level estimate of the previous period plus one minus smoothing constant of the trend multiplied by the previous trend level. And here is the forecast. How to find the forecast? It's simply the addition of both. Since it is additive, Holt's exponential smoothing model is additive of level and trend. It's not multiplicative. Here in this Excel sheet, we have a sample sheet of demand for palm oil, and the monthly is on this column A, and the yearly, and this is the demand that is observed throughout the history of the palm oil demand. So here the forecasted demand is this one is the estimate for this is simple exponential smoothing model. This is the estimate, and then here is the equation where we multiply the smoothing constant into the observed demand plus 1 minus smoothing constant multiplied by the previous forecast. For the smoothing constant, it could be changed. You can decide on having it as zero point 0.1, 0.3, or zero point 0.5. There are levels to it. So in this chart, we have the actual demand and the forecast of smoothing constant, smoothing factor that is changed. And as we can see, the ones that are closer to the actual demand is zero point 0.5 smoothing factor. And here we can see from the result as well, the absolute percent error that is found out is decreases over at zero point 0.5 smoothing factor. This is the example of a simple exponential smoothing model. And the next, we are going to look at the Holtz exponential smoothing model, where we have both smoothing constant. The first one for level, we call it alpha, and the trend estimate, the trend smoothing constant, we call it beta. And here again, we have the palm oil demand. This is the level estimate, and the trend is already estimated as well. And from here on, we carry out the forecasting, where we find out the next level, and then here is a trend as well. Later on, you since it is additive, the forecast is level plus trend, and here is the result for it. And this chart shows us the actual demand as well as the forecasting demand. Since there is a seasonality involved as well, it doesn't capture the whole data specifically. But the trend wise, I think it projects is very well. The projection is shown and also the trend is shown as well. So here we're going to talk about initialization of parameters. Points to note is that there is no single best method. All of them are good ones. They just need to be adjusted and to find out which scenario to be used at. So we need to find out before initialization, there is these steps involved before doing any forecasting. So which is initialization of parameters, and then the training, and then testing. So for simple exponential smoothing model, we need to first estimate initial level parameter. To find out the initial level parameter, we use average demand for several periods. Very simple. For Holt model, where we need to find out both level and trend parameters, we use ordinary least square regression of demand for several periods to find out best fit linear equation. Okay, so for doing forecasting, there is like three phases on three different data sets. The first one is the initialization. We need to first estimate the level trend if seasonality is involved as well. We need to find out the parameters. And for training, we use another different data set, and that is to find out the smoothing parameters to use, where you tweak the smoothing parameters. Either it could be zero point 0.1, 0.2, or 0.01. And then finally, we use the different data set for finding out the quality of the forecast, the accuracy and biases as well. For selecting data, it needs to be long and relevant, and it needs to be cleaned. For picking the smoothing parameters, we could see the level that when it's stationary or it's just level only involved. I think that zero point 0.1 is reasonable. You could choose from 0.01 to zero point 0.3. And if there is a trend, you could choose from 0.02 to 0.51. And you could say 0.19 is reasonable. And trend, it could range between, if trend is involved, it could range between 0.005 to 0.176. And I think that in this example, like you could say 0.053 is reasonable. I think that's the end of our topic, exponential smoothing model, and hope you have a nice day.
Now we will be talking about least square methods. So this is a method that's used to approximate a line or curve of best fit for a given set of data. It serves as a visual representation of a relationship between two or more variables. In financial analysis, it is used to find the relationships between a company's stock returns and the returns of an index for which the stock is a component of. it's also used to predict the sales of a company. The most used method is that of linear regression, where a line of best fit is found for a given data set. And this is the simplest method used to predict trends for a given data set. So, um, given a set of data, as shown on the left, the scatter plots, the multiple dots around, a linear relationship can be modeled to fit it. As you can see, the linear line here, given by the equation y equals a sub 0 plus a sub 1 x. However, for each predicted demand in the model, there exists an error with the actual demand. So as you can see here, for sales period 20, the actual demand is around 1,000, but sorry, the predicted demand is 1,000, but the actual demand is around 1,500. So that could be included in the model as R, which we can then rearrange to define R in terms of the actual demand and the model predicted demand. So regression involves the reduction of error for each point. In this case, it reduces R. And the method used is to reduce the sum of the square of the error, hence the name least square method. So the sum of all squares of errors could be given by S, which is equal to sigma of R squared. The minimum is found by solving for when the differential of S equals to 0, differential of S in relation to a sub 0 and a sub 1, which is given as shown here. Now, if we note that sigma a sub 0 is equals to n a sub 0, where n is the number of periods, then we can rearrange the above differentials into the following normal equations. Now, if we solve for this normal equation simultaneously, we can get an expression for a sub 1, the slope of the linear model, which is given by this equation here. And if we note that the average is equals to sum divided by the total number of periods, then we can simplify the equation to be in the form of as shown here, where we have the sum of x multiplied by y minus the number of periods times the product of the average of x and y, and all this divided by the sum of x squared minus number of period times the average of x squared. Okay, and from the expression from solving for a sub 1, we can then include this into the expression to solve for a sub 0. Now with a sub 1 and a sub 0, we can now completely model we now have a proper mathematical expression for the linear model. So to give an example, we'll use the data of monthly demand for palm oil from the years 2012 until 2014. So here we will do two different linear models. One where we forecast for 2013 and 2014, meaning we use data only from 2012. Second is we predict data, the actual demand for 2014 alone, in which case we use the actual demand data from 2012 and 2013. Now, both of these would be compared with a line of best fit that use data from all 3 years. So using 1 year, 2012, the data set is modified as shown below, where we include a period given by x, and we also add the squared of x and the product of x and y being the demand, the actual demand. So using the expression for a sub 0 and a sub 1, we have the following values, and the model is given as shown: y equals 32.192x plus 517.33. So from here, we plot the line of best fit from periods 1 to 36, and here we note that prediction period starts from period 13 up until 36. And as you can see here, there is already noticeable difference at the start of the prediction, and the deviation begins to get more significant as the period goes on. Doing the same for using data from 2012 until 2013, and we note that forecasting begins in period 25 till 26. We have a sub 0 equals 142.53 and a sub 1 equals 24.604. As you can see, the line deviates only slightly from the actual line of best fit and follows it closely. However, you will notice that the deviation does begin to increase as the prediction period goes on. Hence, what we can summarize from this is that the more data that's available and used, the more accurate the predictions will be using linear regressions. And the deviation will increase as the prediction period extends further into the future. Hence, why it is advised not to predict too far into the future using linear regressions.
I'm Wong Zijin and I'm representing a moving average. Moving average has the formula of the sum of the previous n periods of data divided by n, where n can be 3 months or 4 months. Moving averages can be said to be the forecast value that uses the actual data in a certain period. It is also the average of the n period most recent data. Moving averages is used to determine the trend and tends to smooth out short-term irregularities in the data. Moving average is useful if market demands remain steady over time, and it is usually used in finance or economic roles in the company to predict market trends, conduct pricing analysis, financial analysis, and engage in stock market activities. This is the table of the palm oil demand in Shah Alam in 2012 of each month. For example, to calculate the 3-month moving average of April, we take the values of the previous 3 months and divide it by 3. Therefore, in this example, the forecast value moving average for April is 560, and this goes the same for the following months. For weighted moving average, the formula is the sum of the weight for period n multiplied by the demand in period divided by the sum of weights. Weighted moving average is used when trend or pattern is present. The weights used are to emphasize on recent values. This method is more responsive to change as the recent values has higher weights. The weights used will be based on experience. In the example to apply weighted moving average, the demand 3 months ago is multiplied by 1 and the demand 2 months ago is multiplied by 2 and the last month is multiplied by 3. And this is divided by the sum of weights which is 6. And this goes the same for the following months where the demands are multiplied according to the weights. So by comparing the 3 months moving average and the weighted 3 months moving average, the weighted one reflect recent values more. And this is the graph for 3 months moving average plotted based on the example. This is the 5 months moving average. So by comparing between the 3 months and the 5 months moving averages graph, we can see that both moving average smooths out sudden fluctuations and provide stable estimates. The 5-month moving average shows a smoother graph which justify that higher intervals can cause bigger smoothing effect. The problems with moving averages is since it causes smoothing effect, it is therefore less sensitive to changes. However, the weighted moving average reacts quicker to changes. Next is that both methods lag behind actual values. And lastly, moving averages require more past data for more accurate forecast values.
Hi, my name is Shamin Ahmed. I'll be presenting the seasonal index. Seasonal indexing is done by computing the highs and lows of each time period into an index. A seasonal index can represent how a particular season compares with average season, which helps management forecast sales. A seasonal index can vary in such way that it can occur within a year or within a shorter time period, such as a month or a week. Recurring variation over time may indicate the need for seasonal adjustment in the trend line. To analyze the seasonal effect, we construct seasonal indices. Seasonal indexes indicates the degree of which the season differ from the average time series value across all seasons. Will be the calculating the seasonal index. As I'm using the same data sets such as the palm oil from the year 2012, 2013, and 2014. Okay, in order to calculate the seasonal index, first you have to calculate the average yearly demand. You just need to compute the average uh, monthly basis on each year. For example, you just have to add the 584 with 720 and 855, add it all together and average it by 3, and you get the average daily demand. You just have to compute all of the average yearly demand for each month. Next, after you compute the average yearly demand, you just have to sum it up, total it up, which finally you get this value. And in order to calculate the average monthly demand for based on a 3 years data set, you just have to divide this value by 12, then you get the average monthly demand. Next, in order to compute the seasonal index, you just have to divide the average yearly demand by with the average monthly. You just, for example, 720 divided by 897, you get the seasonal index for January, which is 0 0.8. In order to get the February, you just have to divide the average yearly demand for February, which is 603, divided by the average monthly 897, you get the seasonal index on February, and so on until you complete your time period. Next, in order to find the forecasting for the year 2015, since we are using three data sets from the year 2012, 2013, 2014, and we can forecast for the year 2015. Total average yearly demand for year 2012, 2013, and 2014 is 10,763. And we just have to forecast for 2015 roughly within that range, preferably a slight more. For this 2015, I just forecasted to be 11,000. And in order to forecast for each month, you just have to calculate the average monthly demand for the forecast. You just have to divide this value by 12 and times the monthly seasonal index that we compute just now. And we can find the value and the forecasting demand for 2015 until December. And next, we can plot the graph based on the actual demand and the forecasting. As you can see here, based on a 3 years data set, the forecasting are roughly average from all the total value of the actual demand. And you can see that this is much the forecasting is much safer as they predict the value to be in between the 3 years data sets average in the middle of the actual demand for the 3 years. As for the conclusion, business forecasting involves making informed guesses about certain business metrics regardless of whether they reflect the specific of a business, such as sales growth or prediction for the economy as a whole. Financial and operational decisions are made based on economics condition and how the future look amid uncertainty. Companies use forecasting to help them develop business strategy. Past data is collected and analyzed so that patterns can be found. Today, big data and artificial intelligence have transformed business forecasting methods. Forecasting can be dangerous and risky as forecasting became a focus for companies and government, mentally limiting their range of action by presenting for the short to long-term future as predetermined. Moreover, forecasting can easily break down due to random elements that cannot be incorporated into a model, or they can be just plain wrong from the start. The easiest example that I can give for this explanation is that during the COVID era in the year 2020, all the forecasting made for that particular year uh, can be unpredictable and useless, as none of the companies can predict such outbreak. However, business forecasting is vital for businesses because it allows them to plan production, financing, and other strategies. And with that, thank you very much.